Okay, so I'm going over the charge homework here, and let's get up here. So it says to draw free body diagrams, and there really should, any body has two free body diagrams actually. So there's the real forces and the components. So I chose to just put the real forces, seems like what they wanted. So we have F Coulomb to the left, since the two balls are basically on the same length of string, the mass is the same, all those things. They're going to both feel an F Coulomb that are going to be equal and opposite. At the moment, they're telling us both charges are equal, but it turns out it doesn't matter because they're free hanging. And so the F Coulomb is whatever it is. You have the two amounts of charge, because remember, F Coulomb is F Coulomb equals KQ1 Q2 over the distance between them. So it doesn't matter what the actual charge on each one is. And they're free hanging, so the F Coulomb on that one exerts on the other is equal and opposite to the other way around, Newton's third law. So then we have the W, the force of gravity, the weight, and then the tension. So both Fc, Coulomb, and the weight are action at a distance or non-contact. So I guess I didn't write that. So this is NC, NC. That's certainly contact. I already put that there. And ANC, right? These are so-called action at a distance, Coulomb force and the force of gravity. Okay, so now they said, all right, we're going to make, everything is going to stay the same, but we're going to reduce the charge a little bit, so that if everything stays the same just as before, the two angles, I labeled them theta 2 and theta 2 prime, they have to be equal to each other because the two whatever the Coulomb force is, it's one exerts it on the other, and vice versa, Newton's third law. And also because everything else is equal, the masses and the length of the string, that also means that the angle theta 2 is going to be less than theta 1 because the F Coulomb is going to be a little bit less, and the the tension is also going to be a little less because you'd have to break it down into components, right? And then this is a static equilibrium problem where you have, let's see, so the components would be F of Coulomb, and there's a tension component, let's say in the horizontal direction, and then there's also the weight, and there's a component of the tension in the vertical direction. And it's a system of equations, right? So because you may not, it depends on what you know, if you're given the angle or you're given the tensions. I suppose if you know F Coulomb and you know the weight, then you should be able to figure out all the rest. Yeah, of course. Because you say, oh, look, there's this horizontal component and then the vertical component, and they're related because they have an angle, right? So you just like Physics 2100. Now, if there's no net charge on one ball, there's no F Coulomb, right? But of course, we do know that we can take a charged rod and pick up tissue paper, or we can actually attract conductive. If the balls are both conductive surfaces, then they actually will be attracted slightly. So if you were to draw the balls that now their angle is like this, and so either the red or the blue would have been acceptable because they will attract each other slightly, and these two angles would be equal to each other. Okay, what's next? So this one, right? It would seem that the capital Q's actually cancel each other out, but F Coulomb, the F net will not be zero in the middle there. So both of them, like the plus Q will repel, and so when we look at this picture, we see that's going to be to the right, and a negative capital Q is going to attract, and we see that's also going to be to the right. So that means that the two vectors are pointed to the same direction. So, and in fact, with zero angle between them, so they just add by simple arithmetic. The magnitude of F positive Q plus the magnitude of F negative Q directly. There's no trigonometry involved. How does Coulomb's law apply? Coulomb's law applies in that you calculate, if you have your point of interest here, or your test charge, if it's for force, so you would have a test charge. For electric field, this will be a point of interest. So you calculate F of K, the plus Q, times plus little q over S squared, and then you calculate each pair, the pair being the test charge and the other charge involved. K, negative capital Q, positive little q, and in this case S squared once again, and then you add them as vectors. You have to always remember, in the case of this is our one-dimensional vectors, so they're a bit easier. And then of course, remember you always add vectors, you don't subtract them. And in this case, both of them are positive direction, so they would add together as a simple sum. Okay, this one. So there's total vectors in each case, huh? So there's some net like that, but they both have vertical and horizontal components, right? Whoops. So then there would be a horizontal component from each one, but the vertical components are in opposite directions. So any vertical components, because of the symmetry, any vertical components are going to cancel. So the one that has the least amount of absolute value of vertical components is going to be the stronger one, and since the angle between them in case B is less, there's going to be less vertical components. And the F net in this case, again, because of symmetry, all depends on the horizontal components, which in this case will always point to the left. And in a similar fashion here, you could just make believe there's two positive charges here, and you could come up with the vertical components for each of them. In this case, you have a vertical, and we guess we should just make these a little longer just so we can see the difference. So each one of those plus q's would have a vertical component, but in this case they're in different places. So one would have the vertical component from here, but one is going to have a smaller one. So that means that the total amount of verticals for D is going to be less than the total amount of verticals for C, right? So I would just add up the magnitudes, and we would see that the one on the right has a little bit less, and so that has to have the stronger force, because that means there's more horizontal components. Got to always think of these things as vector quantities. Here it's a similar thing. In this case, there's 0 vertical components. And I thought, oh, I wrote that out, so, oh, they're not, it's not, the comments aren't showing up. Well, that stinks. Okay. I'd used two different, I started marking this up in Adobe Acrobat Pro, and I guess this other app is not happy. But in any case, this got F here, F of E is greater than F of F, because each one of these charges, other than if there's one, no, there isn't even one. Each one of them is going to have a certain amount of vertical component, whereas here there's no vertical components. And so that's what the comments say, yeah, vertical E is equal to 0. Okay, and here, this is the same thing. This negative Q has no vertical components, whereas in this case, it's instead of being little bits, it's just a continuous distribution. But so that just means, once again, you have a whole bunch of vertical components that get smaller and smaller. And so it just, FP has to be greater than F of the rod, simply because FP has no vertical components at all. And let's see, the magnitude of the net force and the magnitude of FP. Right, so since both of them are going to have a net for this, they're saying this a positive, positive test charge there. Both of them are going to have net forces pointing this way, so F net is going to be greater than either one of them, and that is written there. It just keeps flashing in and out. And then now, if we put the negative Q here, we notice that, one important point is, you see this is S. And so the R here is greater than S. So that means that this thing here is certainly going to have an F pointed this way that's going to oppose these guys. And we already know that the F of the point charge is greater than the this semicircle, so we don't really need that to prove that the F net here is going to be less, because it said magnitude of F net. You see, you got to be a little careful. If this negative Q was closer or bigger, then it could in fact produce a net force that's larger, but going to the right. So but because it's the exact same charge, and it's got a distance that's greater, so remember the 1 over r squared, that means that it can't reverse the F net. It'll just make the magnitude of F net less. And we got a couple more. So in this case, there's lots of symmetries involved here. So one of these is the so-called mirror symmetry, and I don't know if this thing would allow me to draw a line or not. But there is if I put a mirror here, everything above and below this line is exactly the same, right? So basically, and with the symmetry of each of these two arc lengths, I know at some point, this may not be exact, but this one's going to oppose, this one's going to attract. So the F plus is always going to point away, say from some nominal center here. So it's not quite right to just simply draw through there. But it didn't ask me that. All I need to know is that because these two arcs are basically the same except for the plus or the minus, I know their vectors are going to be mirror images of each other also. And so that means that if this one points down to the left, this one's going to point down to the right. And basically, because of all the symmetry, F net's always going to point down. and it didn't ask me about the relative magnitudes. I have to assume that since this guy is in the middle here, maybe in here would be the greatest, but I can't tell. I guess B and C would probably have F nets be equal, and A would be a little bit smaller. Okay, lots of symmetry. Okay, here, right, so the negative charges, mobile charges, are pulled to the left, positive charges pushed to the right. So there'll be some force of attraction here. Yes, there'll be some force of repulsion, but because of the 1 over r squared, the negative n wins, and so you'll feel an attractive force. And you can see plenty of demos. You look it up on YouTube. And because of Newton's third law, equal and opposite. So this one here is but this one's a little hand wavy, like number 5. So you have your mobile charges in the block of metal. The negatives will be pulled to the left, the positives to the right. And yes, you might argue that now I've added an extra bit of attraction between Q0 and the cube, but I've also got I have a little bit of repulsion because of the positive side, but you have to keep, well, yeah, and the negative are gonna, the Q negatives. Oh yeah, basically I guess that the amount of charge pulled to the left should actually equal the amount of charge pulled to the right, because I have the Q0 on one side, positive on one side, and negative on the other side. So you can kind of see that in principle, the force of attraction from the cube might add to it, but it's not the case, because there's a balancing here. But the most important thing you'd have to quote is simply there's no net charge change. So if there's no change in net charge, then the force has to stay the same. Now, in fact, if I put something that wasn't a conductor, the net force would change, because the definition of a dielectric is that these charges can't migrate like this so freely. And it's because they can freely migrate around, you end up with a 0 change in the net charge. When you put a dielectric in there, you do get a change in the net charge. It's pretty weird, and you'll talk about that in lecture, and maybe in activity when we talk about capacitors. Okay, here we go.